What if everything you perceive, the room you're in, your body, the air you breathe, even the thoughts forming in your mind right now, is nothing more than an incredibly sophisticated projection? What if the depth and substance you feel so certain about is actually an illusion, and you're living in what amounts to a cosmic hologram? This isn't the realm of science fiction or mystical speculation. This is cutting-edge theoretical physics, emerging from our deepest understanding of black holes, quantum mechanics, and the fundamental nature of information itself. The holographic principle, born from the brilliant minds who've dedicated their lives to unraveling reality's deepest secrets, suggests something extraordinary: that all the information contained in a volume of space can be encoded on its boundary, like a three-dimensional image projected from a flat surface. Picture a hologram you might have seen perhaps on a credit card or in a museum. When you look at it, you see depth, dimension, objects that appear to exist in three-dimensional space. Yet all of that information is actually stored on a flat, two-dimensional surface. The magic happens through interference patterns of light, mathematical relationships that create the illusion of depth where none physically exists. Now imagine that this principle doesn't just apply to parlor tricks and security features, but to the entire universe itself. That your reality, with all its complexity and richness, might be information encoded on a distant cosmic boundary, projected inward to create the experience of living in three-dimensional space. This possibility emerged not from philosophical pondering, but from hardcore mathematical physics. When Stephen Hawking discovered that black holes emit radiation and eventually evaporate, he created a paradox that threatened to tear apart our understanding of reality. Information, according to quantum mechanics, cannot be destroyed. But what happens to information that falls into a black hole when that black hole evaporates completely? The solution that emerged revolutionized our understanding of space, time, and reality itself. Leonard Susskind and Gerard 't Hooft proposed that the information never actually falls into the black hole at all. Instead, it gets encoded on the black hole's surface, its event horizon, like information stored on the surface of a hologram. From the outside, observer's perspective, nothing ever really falls in. It just gets stretched and encoded on the boundary. This led to a stunning realization. If this is true for black holes, it might be true for the entire universe. All the information that makes up everything you know, every star, every planet, every thought and feeling might be encoded on a distant boundary, projected inward to create the reality you experience. The mathematics that describe this possibility are as beautiful as they are mind-bending. In 1997, Juan Maldacena made a discovery that sent shockwaves through the physics community. He found an exact mathematical correspondence between gravity in a higher dimensional space and quantum field theory on its lower dimensional boundary. This wasn't an approximation or a metaphor, it was a precise mathematical equivalence, two completely different descriptions of reality that give identical results. Tonight, we'll journey through this holographic landscape, exploring how the solid world around you might be nothing more than interference patterns in a cosmic projection. We'll discover how your brain itself might operate on holographic principles, storing and retrieving memories through distributed information networks. We'll examine the experiments that are right now trying to detect the pixelated nature of space-time itself, searching for evidence that we truly live in a projection. As we explore these concepts, let your mind relax into the wonder of it all. The holographic principle doesn't diminish the beauty or meaning of existence. It reveals that reality is far more elegant and interconnected than we ever imagined. Every part contains information about the whole. Every observation you make is part of a vast, cosmic dance of information and consciousness. So breathe deeply and prepare to see through new eyes. Tonight, thank you for joining this exploration of holographic reality. Like and subscribe to Whispering Universes for more journeys into the deepest mysteries of existence. Let the holographic visions guide your dreams tonight. In the 1970s, a young physicist named Stephen Hawking made a discovery that would forever change our understanding of reality. Working with the mathematical tools of quantum field theory and general relativity, Hawking found something that no one expected. Black holes aren't perfectly black. They emit radiation, slowly evaporating like cosmic dewdrops in the morning sun of space-time. This discovery was revolutionary enough on its own, but it led to a paradox so profound that it threatened to tear apart the foundations of physics itself. The paradox was deceptively simple. What happens to information that falls into a black hole when that black hole eventually evaporates completely? According to quantum mechanics, information cannot be destroyed. This isn't just a preference or a convenient assumption, it's a fundamental principle that emerges from the mathematical structure of quantum theory itself. Information can be scrambled, transformed, or hidden, but it must always be preserved in some form. This principle had been tested countless times in laboratory experiments and had never been violated. But black holes seem to violate this sacred principle. When matter falls into a black hole, it appears to carry its information past the event horizon and into the black hole's interior. When the black hole eventually evaporates through Hawking radiation, that radiation appears to be completely random, carrying no trace of the information that originally fell in. The information seems to simply vanish from the universe, which should be impossible. For decades, this information paradox haunted theoretical physicists. Some, including Hawking himself initially, were willing to accept that perhaps information could be destroyed in black holes, requiring a fundamental revision of quantum mechanics. Others refused to give up the principle of information conservation, but couldn't explain where the information went. The solution, when it came, was more radical than anyone had imagined. In the 1990s, Leonard Susskind and Gerard Hooft proposed something extraordinary. The information never actually falls into the black hole at all. Instead, from the perspective of an outside observer, the information gets stuck at the event horizon, stretched and encoded on the black hole's surface, like information stored on a flat computer screen. This wasn't just a clever resolution to a paradox, it revealed something fundamental about the nature of space and dimension itself. Jacob Bekenstein had already shown that the entropy of a black hole, the amount of information it can contain, is proportional not to its volume, as you might expect, but to the area of its surface. This was the first hint that three-dimensional physics might somehow be encoded in two-dimensional information. The holographic principle emerged from these insights like a butterfly from a chrysalis. If black holes store all their information on their two-dimensional surfaces, perhaps this principle extends to all of space-time. Perhaps the three-dimensional universe we experience is actually information encoded on a distant two-dimensional boundary, projected inward like a cosmic hologram. Think about what this means for your experience right now. The sensation of depth as you look around your room, the feeling of your body extending through three-dimensional space, the sense that you exist inside a vast universe. All of this might be a projection from information stored on a boundary so distant that light from it couldn't reach you, even if the universe were infinitely old. This isn't science fiction or philosophical speculation. It's a precise mathematical principle that emerges naturally from our best theories of gravity and quantum mechanics. When you combine Einstein's general relativity with quantum field theory, the holographic principle appears as an inevitable consequence, as natural as the way waves emerge from disturbed water. The beauty of this principle extends beyond its mathematical elegance. It suggests a profound unity between seemingly different aspects of reality. Information theory, quantum mechanics, gravity, and thermodynamics all converge on the same startling conclusion, that the universe might be fundamentally two-dimensional, with the third dimension emerging as a kind of optical illusion created by the interference patterns of information. Consider how this changes the very meaning of existence. If you are truly a holographic projection, then every part of you contains information about the whole. Cut a hologram in half, and each piece still contains the complete image, just with less resolution. Similarly, if the universe is holographic, then every region of space contains information about the entire cosmos, encoded in increasingly subtle patterns. The implications ripple outward like gravitational waves through the fabric of understanding. If space itself is emergent from information patterns, then perhaps time is as well. The flow of moments, the progression from past to future, the very experience of duration, all might be aspects of how information is processed and decoded in the cosmic hologram. As you absorb these concepts, notice how they shift your relationship with the physical world around you. The solid surfaces that seem so real, the air that fills your lungs, the light that reaches your eyes, all might be manifestations of information patterns dancing on a distant boundary. You are not separate from this cosmic hologram. You are an intricate part of it, a conscious pattern capable of recognizing its own holographic nature. The black holes that revealed this secret continue to teach us about reality's deepest structures. They are not cosmic vacuum cleaners devouring everything in their path, but information processors of unimaginable sophistication, encoding the histories of entire stellar systems on their event horizons. They are the universe's way of showing us that what appears solid and three-dimensional might be nothing more than shadows cast by patterns we cannot directly perceive. Tonight, as you drift towards sleep, let these ideas percolate. In 1997, a young theoretical physicist named Juan Maldacena made a discovery that would revolutionize our understanding of reality itself. Working with the complex mathematics of string theory, Maldacena found something extraordinary: an exact correspondence between gravity in a higher dimensional space and quantum field theory on its lower dimensional boundary. This wasn't an approximation or a useful analogy, it was a precise mathematical equivalence. Every calculation performed in the higher dimensional gravitational theory gave exactly the same results as corresponding calculations in the lower dimensional quantum theory. It was as if Maldacena had discovered that two completely different languages were actually the same language written in different scripts. The technical name for this correspondence is the ADC-FT duality, referring to anti-de Sitter space and conformal field theory. But beyond the intimidating acronyms lies a revelation that strikes at the heart of what we mean by reality itself. Maldacena had proven mathematically that a universe with gravity in 5 dimensions is completely equivalent to a universe without gravity in 4 dimensions. Imagine you're looking at a hologram again, but this time understand it through the lens of mathematics. The 3-dimensional image you perceive emerges from interference patterns created by laser light bouncing off a 2-dimensional surface. The mathematical relationship between the flat surface and the 3-dimensional image is precise and deterministic. Every point in the 3D image corresponds to information encoded in the 2D pattern, and every feature of the 2D pattern contributes to the 3D appearance. Maldacena's discovery revealed that this relationship between dimensions isn't just a clever optical trick, it's a fundamental feature of how reality itself is structured. The mathematics showed that you could take any physical process happening in the higher dimensional space, stars forming, black holes colliding, particles interacting, and describe it completely using the physics of the lower dimensional boundary. This means that gravity itself, which Einstein showed us curves space-time and creates the geometry of the universe, might be an emergent property rather than a fundamental force. Just as the 3-dimensional appearance of a hologram emerges from the interference of light waves, gravity might emerge from the information processing patterns occurring on a distant boundary. The mathematical beauty of this correspondence extends far beyond its initial discovery. String theorists have since found thousands of examples of such dualities, each one revealing that what appears to be fundamentally different descriptions of reality are actually equivalent. It's as if the universe has a hidden symmetry, constantly translating between different dimensional descriptions of the same underlying truth. Consider what this means for the nature of space itself. In our everyday experience, space has 3 dimensions: length, width, and height. We move through space, exist within it, and think of it as the stage upon which all physical processes occur. But the holographic principle suggests that this 3-dimensional space might be like the 3-dimensional appearance of a hologram, real and meaningful to us as observers, but fundamentally emerging from information patterns in a lower dimensional space. The mathematics that describes this emergence is breathtakingly elegant. The equations that govern the higher dimensional gravitational physics transform into the equations that govern the lower dimensional quantum physics through what mathematicians call a duality transformation. It's similar to how Fourier transforms can convert between descriptions of waves in time and descriptions of frequencies, the same information expressed in different mathematical languages. This mathematical equivalence has profound implications for our understanding of information itself. In the higher dimensional description, information appears to be distributed throughout a volume of space. But in the lower dimensional description, the same information is encoded on a boundary surface. This suggests that information is more fundamental than space, that space itself emerges from the relationships and patterns in how information is organized and processed. The precision of these mathematical relationships leaves no room for approximation or interpretation. When physicists perform calculations in both descriptions, they get identical results to arbitrary precision. This isn't philosophy or speculation, it's mathematics as rigorous as the calculation of planetary orbits or the prediction of atomic energy levels. The implications extend to the very nature of physical law itself. Laws of physics that appear fundamentally different in different dimensional descriptions are revealed to be the same law expressed in different mathematical vocabularies. Conservation of energy, conservation of momentum, the principle of least action all remain identical across the dimensional transformation, suggesting that these principles reflect something deeper than our usual understanding of three-dimensional physics. The mathematics also reveals something profound about the role of information in physics. In the holographic description, every bit of information on the boundary corresponds to specific features in the higher dimensional space. Change one bit on the boundary, and the entire higher dimensional configuration must adjust accordingly. This suggests a deep connection between information theory and the geometry of space-time itself. This mathematical framework has allowed physicists to solve problems that were previously intractable. Complex calculations in strongly coupled quantum systems, which would be impossible to perform directly, become manageable when translated into their gravitational duals. It's as if mathematicians discovered they could solve difficult problems in algebra by translating them into geometry, solving them there and translating back. The beauty of these mathematical correspondences hints at an even grander unity underlying all of physics. If gravity and quantum mechanics can be shown to be different descriptions of the same underlying reality, perhaps all the forces and particles we observe are simply different aspects of how information patterns and processes manifest in our particular dimensional experience. As you contemplate these mathematical relationships, consider that your own existence might be describable in multiple, equally valid ways. The thoughts in your mind, the sensations in your body, the awareness reading these words all might be aspects of information processing that admits multiple mathematical descriptions, each equally real and valid. The equations themselves become a kind of poetry, revealing hidden symmetries and connections in the structure. In the 1960s, a neuropsychologist named Carl Pribram made an observation that would forever change how we understand memory, consciousness, and the very nature of information storage in biological systems. Pribram was studying patients with brain damage, trying to understand how memories are stored and retrieved in the neural networks of the mind. What he discovered challenged everything scientists thought they knew about how the brain works. Traditional neuroscience assumed that memories must be stored in specific locations within the brain, like files in a filing cabinet or books on a library shelf. If you damaged a particular region, you should lose specific memories associated with that area. But Pribram's patients showed something entirely different. Even when large portions of their brains were damaged, they retained access to complete memories, though often with reduced clarity or detail. This led Pribram to a startling hypothesis. What if the brain stores memories holographically rather than locally? What if each memory is distributed throughout the neural network, with every region containing information about the whole? To understand how this might work, Pribram drew inspiration from the mathematics of holography itself. Dennis Gabor, who won the Nobel Prize for inventing holographic photography, had shown that holographic storage relies on interference patterns the way waves interact when they overlap. When two coherent light waves meet, they create a pattern of constructive and destructive interference that encodes information about both waves' original properties. Pribram realized that neurons communicate through waves of electrical activity, and these waves create interference patterns throughout the brain's neural networks. When you form a memory, the pattern of neural firing creates an interference pattern that gets distributed across many regions of the brain. When you recall that memory, the brain reconstructs the original pattern from these distributed traces. This holographic model of memory explains many puzzling features of how the brain actually works. Like a hologram cut into pieces, where each fragment still contains the complete image, a brain with damaged regions can still access complete memories. The information isn't lost, it's simply accessed with less resolution, like viewing a hologram through a smaller window. The mathematics underlying this process are remarkably similar to those describing quantum field interactions. Neural oscillations in different frequency bands, gamma waves, theta waves, alpha waves, interact through non-linear dynamics that create complex interference patterns. These patterns encode not just individual memories, but the relationships between memories, the context in which they were formed, and the emotional coloring that gives them meaning. Consider what happens when you remember something right now. Perhaps the smell of your grandmother's kitchen, or the feeling of sand between your toes at a beach you visited years ago. According to the holographic model, that memory isn't retrieved from a single storage location. Instead, the neural networks throughout your brain resonate in a pattern that reconstructs the original experience from distributed information traces. This process is remarkably similar to how information is encoded and retrieved in the cosmic hologram we've been exploring. Just as all the information in a volume of space might be encoded on its boundary surface, all the information of your experience might be encoded in the interference patterns of neural activity distributed throughout your brain. The holographic nature of memory also explains the associative quality of human recall. When you remember one thing, it often triggers memories of related experiences, creating cascades of recollection that seem to emerge spontaneously. In a holographic system, every part contains information about the whole, so accessing one memory naturally activates the patterns associated with related memories. Recent neuroscience research has provided striking evidence for the holographic model of brain function. Studies using advanced brain imaging techniques show that memories involve synchronized activity across multiple brain regions, with information encoded in the phase relationships between neural oscillations rather than in the activity of individual neurons. The temporal dynamics of memory also fit the holographic model beautifully. Memories don't simply fade uniformly over time, they transform, with some aspects becoming stronger while others fade away. This is exactly what you'd expect from a holographic storage system, where the interference patterns naturally emphasize the most frequently accessed information while allowing rarely accessed details to fade into the background noise. The holographic brain model also provides insights into the nature of consciousness itself. If your brain operates holographically, then your conscious experience might emerge from the interference patterns of neural activity, just as a three-dimensional image emerges from the interference patterns in a hologram. Your sense of unified awareness, despite the distributed nature of neural processing, becomes a natural consequence of holographic information integration. This connects directly to the larger theme of holographic reality. If the universe itself is holographic, and if your brain processes information holographically, then there's a deep resonance between the structure of your mind and the structure of reality itself. You are not just observing a holographic universe, you are a holographic being capable of recognizing the holographic nature of existence. The implications extend to questions of personal identity and continuity of self. In a holographic brain, your sense of being a continuous person over time emerges from the persistence of distributed information patterns rather than from any single, unchanging component. You are, in a very real sense, a pattern that recognizes itself, a holographic process capable of self-awareness. The creative aspects of human cognition also make more sense from a holographic perspective. When you have insights, solve problems creatively, or make unexpected connections between ideas, you're experiencing the holographic brain's ability to access information from new angles, to reconstruct patterns in novel ways that reveal previously hidden relationships. As you consider these ideas, notice how they transform your relationship with your own mind. Your thoughts, memories, and experiences aren't stored in isolated compartments, but are part of a vast, interconnected web of holographic information processing. Every memory contains traces of every other memory. Every thought emerges from the interference patterns of countless previous experiences. Tonight, as you slip into sleep and dreams, your brain will continue this holographic process. In 1884, a Victorian schoolmaster named Edwin Abbott wrote a small book that would prove to be one of the most prescient works of mathematical imagination ever created. Flatland. A romance of many dimensions told the story of a two-dimensional being living in a flat world, completely unaware that a three-dimensional reality existed beyond his perception. Abbott's protagonist, A. Square, lives his entire life on a flat plane, interacting with other geometric beings, lines, triangles, polygons, all confined to their two-dimensional existence. They have no concept of up or down, no understanding that anything could exist outside their flat reality. When a three-dimensional sphere passes through their world, they perceive it only as a circle that mysteriously grows and shrinks, appearing and disappearing in ways that seem magical and impossible. Abbott intended his book as social satire, but he unknowingly created the perfect metaphor for our possible situation in a holographic universe. Just as the Flatlanders cannot perceive the third dimension, despite living within its influence, we might be unable to perceive the higher dimensional reality from which our three-dimensional experience is projected. The mathematics of dimensional projection that Abbott intuited has become central to modern physics. When a three-dimensional object passes through a two-dimensional plane, the 2D inhabitants see only cross-sections, slices of the higher dimensional reality that seem to change mysteriously over time. Similarly, if we are holographic beings projected from a higher dimensional boundary, we might be seeing only cross-sections of processes occurring in spaces we cannot directly perceive. Consider how this applies to your immediate experience. The room around you, with its apparent depth and three-dimensional structure, might be like the circles that A. Square perceives when a sphere passes through flatland. The solid walls, the space between objects, the very sensation of volume and depth, all might be cross-sectional views of patterns encoded on a distant boundary. The holographic principle suggests that we are, in essence, sophisticated flatlanders. Our three-dimensional universe might be projected from information encoded on a two-dimensional surface located at the edge of our cosmic horizon. This boundary is so far away that light from it couldn't reach us, even if the universe were infinitely old. Yet every piece of information about our reality is encoded there in patterns we cannot directly perceive. The mathematics describing this projection are far more elegant than Abbott could have imagined. In general relativity, the boundary of our observable universe is called the cosmic horizon, the furthest distance from which light has had time to reach us since the Big Bang. According to the holographic principle, all the information contained within this cosmic sphere is encoded on its spherical boundary, like information stored on the surface of a vast cosmic hologram. This encoding works through the same mathematical principles that govern optical holograms. Information about three-dimensional structures is stored in the interference patterns created on a two-dimensional surface. When properly decoded, in our case, through the natural processes of physical law, these patterns create the appearance of depth, volume, and three-dimensional structure. The pixelation of this cosmic hologram occurs at the Planck scale, the smallest possible unit of space and time that physics can meaningfully describe. At this scale, roughly 10⁻⁵ meters, space-time itself becomes granular, composed of discrete units of information. If our reality is truly holographic, then space is literally pixelated at this fundamental level, like a cosmic computer screen with unimaginably tiny pixels. This pixelation has profound implications for our understanding of the nature of space itself. The smooth, continuous space that we experience in our everyday lives emerges from the statistical behavior of vast numbers of Planck-scale pixels, just as the smooth appearance of a photograph emerges from the statistical arrangement of individual dots of ink or pixels on a screen. The boundary encoding all this information operates according to principles that seem almost computational in nature. Each Planck scale area on the cosmic boundary can store exactly one bit of information, a binary choice, yes or no, on or off. The total information content of our observable universe is therefore limited by the surface area of our cosmic horizon, measured in Planck units. This information limit has startling consequences. It means that our universe, despite containing hundreds of billions of galaxies with countless stars and planets, can be completely described by a finite amount of information. Every particle, every interaction, every thought and feeling throughout cosmic history, all of it encoded in the binary patterns on our cosmic boundary. The geometric relationships involved in this projection create some of the most beautiful mathematics in all of physics. The ADS-CFT correspondence that we explored earlier provides the mathematical framework for understanding exactly how information on a boundary can give rise to the experience of living in a higher dimensional space. The equations describe a precise mapping between geometric structures in the bulk space and algebraic structures on the boundary. From our perspective, as inhabitants of this holographic projection, we cannot directly perceive the boundary on which our reality is encoded. We are like A. Square, living within the projection but unable to step outside and see the full dimensional structure that gives rise to our experience. Our scientific instruments, our telescopes and particle accelerators, are themselves part of the holographic projection, so they show us only the projected reality. Yet there are subtle signs that might reveal our holographic nature, just as A. Square might notice strange phenomena. When three-dimensional objects pass through his world, we might detect glitches or artifacts that betray the computational nature of our reality. Some theorists suggest that the mysterious dark energy accelerating cosmic expansion might be related to the information processing limitations of our holographic boundary. The philosophical implications of living in such a projected reality are profound, yet not diminishing. If you are indeed a pattern of information encoded on a cosmic boundary, you are no less real or meaningful than if you were made of ordinary matter in ordinary space. The love you feel, the beauty you perceive, the consciousness that experiences these words all remain equally valid regardless of their ultimate substrate. As Abbott's A. Square learned when the sphere lifted, Albert Einstein famously called it spooky action at a distance, the phenomenon of quantum entanglement that seemed to violate his cherished principle that nothing can travel faster than light. When he, along with colleagues Podolsky and Rosen, proposed their famous EPR paradox in 1935, they were trying to show that quantum mechanics must be incomplete. How could particles separated by vast distances instantaneously affect each other's properties? Einstein was certain that quantum entanglement revealed a fundamental flaw in quantum theory. There must be hidden variables, he argued, some underlying reality that predetermined the behavior of entangled particles, making their correlated behavior only appear instantaneous. The universe, Einstein believed, was locally realistic. Objects could only be influenced by their immediate surroundings, and their properties existed independently of observation. But the universe had other plans. In the 1960s, physicist John Bell proved mathematically that any theory based on local hidden variables would make predictions that differed from quantum mechanics. When experimenters finally tested Bell's inequalities in the 1980s and beyond, the results were clear. Quantum mechanics was correct, and Einstein's local realism was wrong. The universe really does exhibit what we now call quantum non-locality. This discovery has profound implications for our understanding of reality, but it took until the 21st century for physicists to realize just how profound. Quantum entanglement isn't just a curious feature of microscopic particles, it might be the very fabric from which space-time itself is woven. The connection between entanglement and space-time geometry was first glimpsed through studies of black holes. When matter falls into a black hole, it becomes entangled with the matter that remains outside. This entanglement creates what physicists call an entanglement shadow, a region where quantum correlations become increasingly complex and difficult to disentangle. The mathematics describing these entanglement patterns revealed something extraordinary. The geometry of space-time around a black hole is directly related to the pattern of quantum entanglements between matter inside and outside the event horizon. Regions of space that are closely connected geometrically correspond to matter that is highly entangled quantum mechanically. This led to one of the most startling discoveries in modern physics, the ER equals EPR correspondence, proposed by Leonard Susskind and Juan Maldacena. Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen entanglement are not just similar phenomena, they are the same phenomenon described in different languages. Quantum entanglement literally creates the geometry of space-time. Think about what this means for the holographic principle. If space-time geometry emerges from quantum entanglement patterns, and if these patterns can be described holographically on a boundary surface, then entanglement becomes the mechanism by which the holographic projection creates the experience of living in three-dimensional space. The mathematical framework describing this process is breathtakingly elegant. Quantum entanglement can be measured by a quantity called entanglement entropy, which describes how much information is shared between different regions of a quantum system. The remarkable discovery is that this entanglement entropy is geometrically equivalent to the area of surfaces in the holographic space. This connection runs deeper than mere analogy. The actual equations that describe entanglement entropy in the boundary theory are mathematically identical to the equations that describe geometric areas in the bulk space. change the entanglement pattern on the boundary, and the geometry of space itself changes accordingly. The universe becomes a vast quantum computer, with space-time emerging from information processing at the cosmic boundary. The implications for our understanding of consciousness are profound. If your brain operates through quantum processes, and increasing evidence suggests that it does, then your thoughts and experiences are connected to the fundamental entanglement network that creates space-time itself. Your consciousness doesn't just observe the universe, it participates in the quantum information processing that gives rise to reality. Recent experiments in quantum information science have demonstrated that entanglement can be used to transmit information in ways that seem to transcend the normal limitations of space and time. Quantum teleportation, quantum error correction, and quantum cryptography all rely on entanglement networks that process information non-locally. These technologies give us a glimpse of how the universe itself might operate as a vast quantum information processor. The holographic principle suggests that the entanglement network creating our reality extends from the quantum scale to the cosmic scale. Every quantum interaction in your body, every synaptic firing in your brain, every photon absorption in your retina connects to the vast web of entanglement that spans the observable universe. You are not separate from this cosmic information network, you are a conscious node within it. The non-local nature of quantum entanglement also provides a mechanism for the kind of instantaneous correlation across vast distances that a holographic universe would require. Information changes on the cosmic boundary can immediately affect the entire holographic projection, not because signals travel faster than light, but because the entanglement correlations are already established across all scales. This quantum foundation of reality also explains some of the mysterious features of consciousness itself. The unified nature of subjective experience, the way diverse sensory inputs combine into a single stream of awareness, might reflect the holistic properties of quantum entanglement networks. Just as entangled particles share a unified quantum state regardless of their spatial separation, the distributed neural processes in your brain might share unified quantum states that give rise to the unity of consciousness. The temporal aspects of entanglement also connect to the holographic nature of time itself. Quantum entanglement can create correlations that extend backward and forward in time, suggesting that the temporal ordering we experience might be an emergent feature of how information is processed in the cosmic hologram rather than a fundamental aspect of reality. As you contemplate these ideas, consider that the quantum entanglement networks we've been discussing aren't abstract mathematical constructs, they're the actual physical mechanism, creating your moment-by-moment experience of existence. Every thought, every sensation, every moment of awareness emerges from quantum information processing in networks that extend from the synapses in your brain to the cosmic boundary of the observable universe. Tonight, as you drift towards sleep, at this very moment, approximately 46.5 billion light-years away from you in every direction, there exists a boundary beyond which you can never see, never visit, and never receive information. This is your cosmological horizon, the edge of your observable universe, and according to the holographic principle, it might be the most important surface in all of existence. This cosmic boundary isn't empty space or a physical wall. It's a spherical surface defined by the fundamental geometry of space-time itself, created by the interplay between the expansion of the universe and the finite speed of light. Light from beyond this horizon hasn't had enough time to reach us since the Big Bang, creating a natural boundary to our observable reality. But the holographic principle suggests that this horizon is far more than just an observational limit. It might be the two-dimensional surface on which all the information of our three-dimensional reality is encoded, a cosmic hologram of unimaginable size and complexity, containing the complete description of everything we see, experience, and are. To understand the scale of this cosmic projection, consider that the surface area of our holographic horizon is approximately 10^123 square Planck units. Each of these units can store exactly 1 bit of information, giving our observable universe a total information capacity of about 10^123 bits. This number is so vast that it exceeds the number of atoms in the observable universe by a factor of roughly 10^60. Yet, according to the holographic principle, This finite amount of information is sufficient to encode everything, every galaxy, every star, every planet, every living being, every thought and feeling that has ever existed within our cosmic horizon. The three-dimensional reality we experience emerges from the interference patterns created by information stored on this distant boundary. The mathematics describing this cosmic hologram draws from the same principles that govern ordinary optical holograms, but scaled up to cosmic proportions. Information is stored in the phase relationships between wave patterns on the boundary surface. When these waves interfere with each other according to the laws of physics, they create the appearance of three-dimensional structure extending inward from the boundary. The most remarkable feature of this cosmic hologram is its dynamic nature. Unlike a static photograph, the information on our cosmological horizon is constantly changing as the universe evolves. New information is continuously being written to the boundary as physical processes occur within our observable universe, while other information may be gradually erased or transformed. This dynamic encoding process might be related to the mysterious phenomenon of dark energy, the unknown force that's causing the expansion of the universe to accelerate. Some theories suggest that dark energy represents the energy cost of maintaining and updating the holographic information on our cosmic boundary. As the universe expands and more information needs to be processed, more dark energy is required to power the cosmic computation. The relationship between our cosmological horizon and the cosmic microwave background radiation, CMB, provides another fascinating connection to holographic reality. The CMB represents the oldest light we can observe, coming from the time when the universe first became transparent, about 380,000 years after the Big Bang. This radiation creates a spherical shell of information surrounding us, like the ultimate projection screen for the cosmic hologram. The tiny temperature fluctuations in the CMB variations of only a few millionths of a degree might represent the fundamental information patterns from which all large-scale structure in the universe emerges. These fluctuations, mapped with exquisite precision by satellites like Planck and WMAP, could be the holographic encoding that gives rise to the galaxies, stars, and planetary systems we observe today. The accelerating expansion of the universe adds another layer of complexity to our holographic horizon. As dark energy drives cosmic expansion to accelerate, distant galaxies are being pushed beyond our cosmological horizon at an ever-increasing rate. From our perspective, these galaxies fade away and disappear, their information apparently lost forever. But the holographic principle suggests a different interpretation. The information describing these distant galaxies doesn't disappear. It gets encoded on our retreating horizon as they cross the boundary. Like images preserved in a hologram, even after the original objects are removed, the complete information about these cosmic structures remains encoded on our horizon surface, even after they've passed beyond our ability to observe them directly. This process creates a kind of cosmic memory bank. Our holographic horizon contains not just information about what we can currently observe, but information about everything that has ever been within our cosmic sphere of influence. The entire history of our observable universe is preserved in the holographic encoding on this distant boundary. The geometry of this cosmic hologram also influences the fundamental constants that govern physics within our universe. The relationships between the strength of gravity, the speed of light, Planck's constant, and other fundamental parameters might be determined by the information processing capacity of our holographic boundary. Change the size or structure of the boundary, and the laws of physics themselves might change accordingly. Recent observations of the cosmic expansion rate have revealed puzzling discrepancies that cosmologists call the Hubble tension. Different methods of measuring the expansion rate give slightly different results, suggesting that our understanding of cosmic evolution might be incomplete. Some theorists propose that these discrepancies might be signatures of the holographic nature of space-time, quantum fluctuations in the boundary information that create small but measurable effects in how we observe cosmic expansion. The finite information capacity of our holographic horizon also places fundamental limits on the complexity that can exist within our observable universe. There's a maximum number of bits available to encode all possible physical processes, imposing ultimate bounds on computation, consciousness, and complexity. We are living within an information processing system of finite but enormous capacity. As you contemplate your place within this cosmic hologram, consider that you are not just observing this system from the outside, you are an integral part of it. Your consciousness, your thoughts, your very existence contributes to the information patterns encoded on our cosmic boundary. You are simultaneously a conscious observer of the holographic universe and a conscious component of the hologram itself. The boundary that limits your observable universe is not a prison but a canvas. In the 1980s, a brilliant physicist named Edward Fredkin proposed something that sounded like science fiction but was grounded in rigorous mathematical thinking. What if the universe, at its deepest level, isn't made of matter and energy at all, but of pure information? What if reality is literally computational, a vast digital process running on the hardware of space-time itself? Fredkin's "it from bit" hypothesis suggested that every physical quantity, every particle, every force, and every interaction can ultimately be reduced to binary choices, yes or no answers to fundamental questions about the state of reality. In this view, the universe becomes a gigantic computer, with physical laws serving as the algorithms that process cosmic information. This wasn't merely a philosophical speculation. Fredkin had discovered that many fundamental processes in physics could be perfectly modeled by simple computational rules. Cellular automata, grid-based systems, where each cell's future state depends only on its current state, and the states of its neighbors, could generate behaviors that looked remarkably like the patterns we observe in nature. Stephen Wolfram later expanded this vision in his massive work, A New Kind of Science, demonstrating that simple, computational rules could generate extraordinary complexity. Starting with basic cellular automata, Wolfram showed how rule-based systems could produce patterns that resembled everything from snowflakes to neural networks to galaxy formation. The implication was staggering. Perhaps the universe doesn't follow mathematical laws. Perhaps it is a mathematical computation. The connection to holographic physics becomes clear when we consider how information is processed in computational systems. In any computer, information is stored in memory and processed according to programmed instructions. But the actual computational work, the transformation of input data into output results, occurs at the interfaces between different components of the system. Similarly, in a holographic universe, the computation that creates our three-dimensional reality occurs at the interface between the boundary surface and the bulk space. The boundary stores the information, like computer memory, while the physical laws of the bulk space serve as the algorithms that process this information into the rich, complex reality we experience. This computational perspective provides a new way of understanding the fundamental constants of physics. In a digital universe, these constants would be like the basic parameters of a cosmic computer program, the values that determine how information is processed and how patterns evolve over time. The speed of light becomes the clock rate of the cosmic computer, setting the maximum speed at which information can be processed and transmitted. Planck's constant, which governs the granular nature of quantum mechanics, becomes the minimum unit of information processing, the quantum bit, or qubit, of the cosmic computation. The seemingly random behavior of quantum mechanics might actually be the result of deterministic computational processes occurring at a level too fundamental for us to observe directly. The holographic principle fits perfectly into this computational framework. If our three-dimensional reality is projected from information stored on a two-dimensional boundary, then the projection process itself is a form of computation. The boundary contains the data, and the laws of physics provide the algorithms that compute the three-dimensional appearance from this two-dimensional information. This computational nature of holographic reality might explain some of the most puzzling features of quantum mechanics. The measurement problem why quantum systems seem to exist in multiple states until observed could be understood as a computational optimization. Rather than computing all possible outcomes continuously, the cosmic computer only calculates specific results when they're actually needed, when measurements occur. Quantum entanglement, with its spooky action at a distance, becomes more natural in a computational universe. Entangled particles don't need to send signals to each other across space. They're simply different aspects of the same computational process, like different variables in the same computer program that are naturally correlated because they arise from the same underlying calculation. The many worlds interpretation of quantum mechanics also finds a natural home in computational reality. Rather than an infinite number of parallel universes, we might have a single cosmic computation that explores multiple possible outcomes simultaneously, like a quantum computer running multiple calculations in parallel through superposition. Recent developments in quantum computing have revealed deep connections between computation and the structure of spacetime itself. Quantum error correction, the method used to protect quantum information from noise and decoherence, uses mathematical techniques that are identical to those describing the holographic principle. The codes that preserve quantum information in quantum computers are the same mathematical structures that describe how information is preserved in black holes and cosmic horizons. This suggests that the universe might literally be a quantum computer, with spacetime serving as a natural quantum error-correcting code. The apparent stability of physical laws and constants might result from the universe's built-in ability to correct errors and maintain information integrity across cosmic scales. The computational perspective also provides new insights into the nature of time. In a computational universe, time isn't a dimension through which we move, it's the sequence of computational steps by which the cosmic computer updates the state of reality. Each moment corresponds to one iteration of the cosmic algorithm, computing the next state of the universe from its current state. This computational view of time explains why time appears to flow in only one direction. Computation is inherently directional. Input leads to processing, leads to output. The arrow of time emerges naturally from the irreversible nature of information processing, even if the underlying physical laws are time-symmetric. The limits of computational complexity also place constraints on what can exist within our universe. There are mathematical problems that no computer, no matter how powerful, can solve efficiently. These computational limits might manifest as fundamental physical limits, bounds on the complexity of structures that can exist, the precision with which physical quantities can be measured, or the predictability of complex systems. As you consider your own existence within this computational framework, realize that your consciousness might be an emergent property of the cosmic computation itself. Your thoughts, memories, and experiences could be patterns of information processing that have become complex enough to recognize their own computational nature. The beauty of this perspective is that it doesn't diminish the wonder or meaning of existence. It reveals that consciousness. You've almost certainly encountered holographic images in your daily life, though you might not have recognized the profound physics hidden within these seemingly simple optical illusions. That shimmering rainbow pattern on your credit card, the three-dimensional image floating in a museum display, the security features on currency, all of these demonstrate the same fundamental principle that might govern the entire universe. To truly understand how our reality could be holographic, we need to examine how these everyday holograms work and why their mathematical principles scale up to cosmic proportions. When you look at a hologram, you're witnessing one of the most elegant demonstrations of how information in fewer dimensions can create the appearance of greater dimensional complexity. The creation of a hologram begins with a process called interferometry. Laser light, with its perfectly coherent waves, is split into two beams. One beam bounces off the object being recorded, while the other serves as a reference beam. When these two beams reunite on the recording surface, they create an interference pattern, areas where the waves add together constructively, creating bright spots, and areas where they cancel each other destructively, creating dark spots. This interference pattern looks nothing like the original object. It appears to be a random collection of swirls, dots, and lines completely meaningless to the naked eye. Yet encoded within this seemingly chaotic pattern is complete information about the three-dimensional structure, texture, and appearance of the original object. The hologram has transformed spatial information into an abstract mathematical relationship stored on a flat surface. When you illuminate this recorded pattern with the proper reference beam, magic happens. The interference pattern diffracts the light in precisely the right way to reconstruct the original three-dimensional image. Light rays emerge from the hologram at exactly the same angles they would have come from the original object, creating a perfect illusion of three-dimensional presence. The most remarkable property of this process is its distributed nature. Unlike a photograph, where each point on the image corresponds to a specific point on the subject, every point on a hologram contains information about the entire original object. Cut a photograph in half, and you lose half the image. Cut a hologram in half, and you still have the complete image, though with reduced resolution. This distributed storage property is what makes the holographic principle so powerful when applied to physics. If the universe operates holographically, then every region of space contains information about the entire cosmic structure, just at different levels of resolution. The boundary of our observable universe might contain complete information about everything within it, encoded in interference patterns we cannot directly perceive. The mathematics underlying holographic reconstruction are surprisingly similar to those describing quantum mechanical wave functions. Both involve complex numbers that encode amplitude and phase information. Both rely on interference effects to create observable phenomena, and both demonstrate how abstract mathematical relationships can give rise to concrete physical experience. Modern holographic technology has moved far beyond simple optical illusions. Digital holography uses computer algorithms to calculate interference patterns without needing actual laser light and physical objects. These computed holograms can display objects that never existed in physical form, create impossible geometric structures, and manipulate the apparent properties of light itself. The storage density of holographic systems is extraordinary. A single holographic crystal can store the equivalent of thousands of DVDs worth of information, with every bit distributed throughout the entire volume of the storage medium. This distributed storage provides natural error correction damage too. Part of the system doesn't destroy information, but only reduces its clarity. Real-time holographic displays are beginning to appear in advanced research laboratories, creating three-dimensional images that can be viewed from multiple angles without special glasses or viewing devices. These systems process enormous amounts of information to calculate the interference patterns needed to create convincing three-dimensional illusions in real time. The artistic applications of holography reveal something profound about human perception and the nature of visual reality. Artists working with holograms discover that they're not just creating images, they're manipulating the fundamental relationships between light, space, and observation. Holographic art pieces can create impossible visual experiences, objects that seem to exist in multiple spaces simultaneously, or images that change based on the viewer's position and movement. Security applications of holography demonstrate how difficult it is to reproduce the complex mathematical relationships encoded in holographic patterns. The three-dimensional structures, rainbow effects, and viewing angle dependencies of security holograms make them nearly impossible to counterfeit using conventional printing or copying methods. The parallels to cosmic holography become clearer when we consider the role of the observer in holographic systems. A hologram contains potential images that only become actual when viewed from specific angles with proper illumination. Similarly, if our universe is holographic, the reality we experience might represent one particular viewing angle on a more complex dimensional structure. The wavelength dependence of holographic images also provides insight into the scale-dependent nature of holographic reality. Illuminate a hologram with different wavelengths of light, and you see different aspects of the encoded information. In cosmic holography, different energy scales of observation might reveal different aspects of the underlying reality encoded on our cosmic boundary. Recent advances in metamaterials and photonic crystals are creating holographic systems that operate across the entire electromagnetic spectrum, from radio waves to X-rays. These broadband holographic systems suggest that the principle of holographic information encoding might be far more universal than originally thought, operating across all scales of physical reality. As you observe holographic effects in your daily life, the security features on your identification cards, the three-dimensional displays in museums, have the rainbow patterns created by soap bubbles or oil films, remember that you're witnessing demonstrations of the same mathematical principles that might govern reality itself. The elegant relationship between interference patterns and three-dimensional appearance that creates these everyday illusions might be the fundamental mechanism by which the universe creates the illusion of dimensional depth. Tonight, when you encounter any shimmering in a laboratory beneath the cornfields of Illinois, scientists have built one of the most sensitive measuring devices ever constructed. The holometer at Fermilab isn't searching for new particles or exotic matter. It's looking for something far more fundamental, evidence that space-time itself might be pixelated. That reality might be digital at its deepest level. The holometer represents humanity's first serious attempt to experimentally test whether we live in a holographic universe. Using interferometry techniques similar to those that detect gravitational waves, this remarkable instrument searches for tiny fluctuations in the fabric of space-time itself, quantum noise that would be present if space and time are fundamentally granular rather than smooth. The principle behind the holometer is elegantly simple. If space-time is truly holographic, then at the Planck scale, roughly 10⁻35 meters, space should become pixelated, like zooming into a digital photograph until you can see the individual pixels. These quantum pixels would create a fundamental uncertainty in the measurement of position and distance, a background noise that would affect any sufficiently sensitive experiment. The challenge is that this quantum noise is unimaginably small. The fluctuations the holometer seeks are 10 trillion times smaller than the width of a proton. Detecting such tiny effects requires isolation from every possible source of external vibration, truck traffic, seismic activity, even the motion of clouds overhead. The instrument operates in a carefully controlled environment, with laser interferometry precise enough to detect positional changes, smaller than 1/10th the width of a proton. The first results from the holometer were both disappointing and encouraging. Disappointing because the instrument detected no clear evidence of space-time pixelation at the sensitivity levels originally predicted. Encouraging because this null result placed the tightest constraints ever achieved on the granular nature of space-time, ruling out several models of quantum gravity and providing crucial guidance for theoretical physicists. But the absence of evidence isn't evidence of absence. The holographic principle operates across a vast range of possible scales and mechanisms. The holometer's failure to detect pixelation at one particular scale doesn't rule out holographic reality, it simply refines our understanding of how such a reality might operate. Other experiments have provided tantalizing hints that something unusual might be happening at the intersection of quantum mechanics and space-time geometry. The GO600 gravitational wave detector in Germany has consistently detected a mysterious noise source that shouldn't exist according to conventional physics. This noise appears at frequencies that would be expected if space-time were fundamentally granular at scales much larger than the Planck scale. The noise detected by GO600 has resisted all attempts at conventional explanation. It's not seismic activity, not electromagnetic interference, not thermal fluctuations from the equipment. Some theorists have proposed that this mysterious noise might be our first direct detection of the holographic nature of space-time quantum fluctuations in the cosmic information processing that creates our three-dimensional reality. Advanced gravitational wave detectors like LIGO and Virgo have also contributed to our understanding of space-time's fundamental nature. These instruments can detect distortions in space-time that are smaller than 1/10th the width of a proton, making them sensitive to quantum effects that would be completely invisible to other types of experiments. When these detectors observe the collision of black holes or neutron stars, they're not just detecting gravitational waves, they're probing the behavior of space-time under the most extreme conditions in the universe. The precise waveforms of these gravitational signals provide tests of general relativity and quantum mechanics at energy scales that can't be reproduced in any laboratory. Some of the gravitational wave signals detected by LIGO have shown subtle deviations from the predictions of classical general relativity. While these deviations are within the expected range of measurement uncertainty, they hint at possible quantum corrections to Einstein's theory, modifications that might emerge naturally if space-time is fundamentally holographic. Quantum information experiments have also contributed to our understanding of holographic reality. Laboratory demonstrations of quantum entanglement, quantum teleportation, and quantum error correction use mathematical techniques that are identical to those describing the holographic principle. These experiments prove that the strange, non-local correlations required for holographic reality actually exist in nature. Recent experiments with quantum error-correcting codes have shown that information can be preserved and recovered even when parts of a quantum system are completely destroyed. This demonstrates the distributed information storage that characterizes holographic systems, the same property that allows holograms to be cut into pieces while retaining the complete image. Atomic interferometry experiments, using individual atoms as ultra-precise sensors, have begun to approach the sensitivity needed to detect space-time granularity. These experiments use the quantum properties of matter itself to measure tiny changes in gravitational fields and space-time curvature, providing another avenue for detecting the quantum nature of space-time. The cosmic microwave background radiation serves as a natural laboratory for testing holographic principles on the largest possible scales. The tiny temperature fluctuations in this ancient light encode information about the quantum state of the universe when it was only 380,000 years old. Some theories predict that holographic effects should leave subtle signatures in these fluctuations patterns that would reveal the computational nature of cosmic evolution. Future experiments promise even greater sensitivity to holographic effects. The next generation of gravitational wave detectors will be sensitive to frequencies and amplitudes that could reveal quantum gravitational effects. Space-based interferometers, free from Earth's seismic noise, will achieve unprecedented precision in measuring the geometry of space-time. Quantum computing experiments are also beginning to simulate holographic systems directly. By creating quantum circuits that implement the mathematical relationships of holographic dualities, researchers can study how information behaves in holographic systems and test whether the computational requirements of holographic reality are physically realizable. The search for holographic reality represents a new kind of experimental physics, one that probes not just the contents of the universe, but its fundamental information processing structure. These experiments ask not just, what is reality made of, but how is reality computed? As these experiments continue to push the boundaries of precision and sensitivity, they bring us closer to answering one of the most profound questions in all of science. Are we living in a holographic projection, conscious patterns in a cosmic computation that extends far beyond our three-dimensional experience? The hard problem of consciousness, how subjective experience arises from objective physical processes, becomes even more intriguing when viewed through the lens of holographic reality. If the universe itself is a projection of information from a distant boundary, what does this mean for the phenomenon of awareness that allows you to experience this projection? Consciousness has long puzzled scientists and philosophers because it seems to possess properties that are difficult to reconcile with our usual understanding of physical processes. Your subjective experience feels unified, despite arising from billions of separate neural processes. It seems to exist in the present moment, despite being constructed from memories of the past and anticipations of the future. It appears to be private and internal, despite depending entirely on physical processes that are public and external. The holographic principle offers new insights into these puzzling features of consciousness. In a holographic system, information is distributed throughout the entire structure, with each part containing information about the whole. Similarly, consciousness might arise from information integration processes that naturally create unified experience from distributed neural activities. Recent theories in neuroscience propose that consciousness emerges when information becomes integrated across different brain regions, when separate processing systems begin to share and coordinate their activity in complex. This integration process has mathematical properties remarkably similar to those found in holographic systems. Integrated information theory, developed by Giulio Tononi and others, suggests that consciousness corresponds to integrated information, the amount of information generated by a system above and beyond its individual parts. This theory provides a mathematical framework for understanding consciousness that connects directly to information theoretic descriptions of holographic systems. If the universe is holographic, then consciousness might be the natural way that information integration occurs within the cosmic hologram. Your awareness could be understood as a localized region where the holographic information processing becomes sufficiently complex and integrated to generate subjective experience. This perspective helps explain the binding problem, how the brain creates unified perceptual experiences from separate sensory inputs. In a holographic brain operating within a holographic universe, binding occurs naturally through the interference patterns that create holographic representations. Different sensory inputs combine into unified experience the same way that different light waves combine to create unified holographic images. The holographic nature of memory also connects to the holographic properties of consciousness. Your memories aren't stored in specific locations, but are distributed throughout neural networks, reconstructed each time you remember something. This distributed storage creates the seamless integration between memory and present experience that characterizes conscious awareness. The temporal aspects of consciousness, the way awareness seems to exist in an eternal now despite being constructed from temporal processes, also make more sense in a holographic framework. If time itself is emergent from the information processing that creates the holographic projection, then consciousness might be the mechanism by which temporal information is integrated into the experience of a present moment. Quantum theories of consciousness, such as those proposed by Roger Penrose and Stuart Hameroff, suggest that consciousness involves quantum processes in the brain's microtubular structures. If these theories are correct, then consciousness would be directly connected to the quantum information processing that might underlie holographic reality. The role of observation in quantum mechanics, the way measurement seems to collapse quantum superpositions into definite states, might be related to consciousness in a holographic universe. Conscious observation could be the mechanism by which potential information encoded on the cosmic boundary becomes actual experience in the holographic projection. This suggests a profound connection between consciousness and the fundamental structure of reality. Rather than consciousness being an accidental byproduct of complex information processing, it might be an essential feature of how holographic reality operates. The universe might require conscious observers to complete the process of transforming potential information into actual experience. The unity of consciousness, the way all your diverse sensory experiences, thoughts, and feelings combine into a single stream of awareness, reflects the holistic properties of holographic information storage. Just as every part of a hologram contains information about the whole image, every moment of consciousness might contain information about your entire experiential history. The privacy of consciousness, the fact that your subjective experience seems accessible only to you, also finds natural explanation in holographic terms. Your consciousness might correspond to a specific pattern of information integration that occurs only within your particular neural network. Other conscious beings would have their own integration patterns, creating their own private subjective worlds within the same holographic reality. The apparent unity of consciousness across time, the sense that you are the same conscious being from moment to moment, despite the constant changes in your brain and body, might reflect the persistent patterns of information integration that maintain continuity in holographic systems. Like a holographic image that maintains its appearance despite changes in viewing angle, your conscious identity might maintain continuity despite changes in the underlying neural processes. Free will, one of the most puzzling aspects of consciousness, takes on new meaning in a holographic universe. If the future is not predetermined but emerges from the ongoing information processing of the cosmic hologram, then conscious choice might be a real causal process, a way that integrated information systems influence the development of holographic reality. The social dimensions of consciousness, the way conscious beings can share experiences, communicate, and understand each other, might reflect the interconnected nature of holographic information processing. If all consciousness arises within the same cosmic hologram, then the apparent separation between different conscious minds might be less fundamental than it appears. Altered states of consciousness, dreams, meditation, psychedelic experiences might provide windows into the holographic nature of awareness. In these states, the normal boundaries of conscious experience often dissolve, revealing more fluid relationships between self and other, past and future, internal and external. These experiences might show us how consciousness operates when freed from its usual holographic constraints. As you consider your own consciousness from this holographic perspective, notice how it transforms your relationship with awareness itself. You are not just a passive observer of a holographic universe, you are The holographic principle, profound as it is, becomes even more extraordinary when we consider its implications for the multiverse. The possibility that our universe is just one of countless realities existing within a vast, higher dimensional space. If our three-dimensional universe is a holographic projection from a two-dimensional boundary, what exists beyond that boundary? And could there be other projections, other holographic realities, existing alongside our own? String theory, the most ambitious attempt to unify all of physics into a single mathematical framework, suggests that our universe exists within a higher dimensional space called the bulk. In this picture, our entire cosmos, with all its galaxies, stars, and planets, is like a holographic movie projected from information stored on the boundary of this bulk space. But if one holographic projection can exist, why not many? The mathematics of string theory suggests that the bulk space could support numerous holographic boundaries, each projecting its own three-dimensional reality. These parallel holographic universes would exist in the same higher dimensional space, but would be completely separate from each other, like different movies playing on different screens in a cosmic multiplex theatre. The landscape of string theory, as physicists call it, contains an enormous number of possible vacuum states, perhaps 500 different ways that the extra dimensions of string theory could be configured. Each of these configurations would create different physical laws, different values for fundamental constants, and different holographic projections of reality. In this holographic multiverse, our universe would be just one member of an inconceivably vast collection of realities. Some of these parallel holographic universes might be very similar to ours, with only tiny differences in physical constants or initial conditions. Others might be radically different, with different numbers of spatial dimensions, different fundamental forces, or completely alien forms of matter and energy. The eternal inflation theory, in cosmology, provides another mechanism for generating multiple holographic realities. According to this theory, the Big Bang that created our universe was just one bubble of space-time nucleating within an eternally inflating background. This process continues forever, creating an infinite number of bubble universes, each potentially governed by its own holographic boundary. Each bubble universe in eternal inflation would have its own cosmic horizon, its own two-dimensional boundary on which the information of that reality is encoded. The holographic principle would apply independently to each bubble, creating a multiverse of holographic projections extending throughout the inflating background spacetime. The anthropic principle takes on new significance in a holographic multiverse. If countless different holographic realities exist with different physical laws and constants, then the particular values we observe in our universe might be explained by the simple fact that we exist to observe them. Only holographic universes, with the right conditions for complexity, structure formation, and ultimately consciousness, would contain observers capable of wondering about their holographic nature. This raises profound questions about the nature of consciousness and identity across the holographic multiverse. If information about your consciousness is encoded on the boundary of our cosmic horizon, could similar patterns exist on the boundaries of other holographic universes? Could there be versions of you experiencing reality in countless other holographic projections? The quantum many-worlds interpretation takes on new meaning when combined with holographic multiverse concepts. Rather than an infinite splitting of a single reality, many worlds might describe how a single holographic boundary can encode multiple potential realities simultaneously. Quantum superposition might be the way that one boundary can project multiple universe movies at the same time. The mathematical relationships between different holographic universes could be extraordinarily complex. Just as different holograms can be stored on the same recording medium and accessed by illuminating it with different reference beams, multiple universe projections might be encoded on higher dimensional boundary structures, accessible through different modes of cosmic information processing. Communication between holographic universes would be fundamentally impossible through normal physical means, since each universe is complete and self-contained within its own projection. However, the information theoretic connections through the higher dimensional bulk space might allow for subtle influences between neighboring holographic realities. Dark energy, the mysterious force accelerating cosmic expansion, might be related to interactions between our holographic universe and neighboring ones. The energy driving expansion could come from information processing activities in the bulk space that supports multiple holographic projections, with each universe contributing to and drawing from a shared pool of computational resources. The fine-tuning problems that have puzzled cosmologists, why the constants of physics seem perfectly adjusted for complexity and life find natural resolution in a holographic multiverse. With countless different projections, exploring every possible set of physical laws, the existence of realities like ours becomes statistically inevitable rather than mysteriously improbable. The holographic multiverse also provides new perspectives on the nature of mathematics and physical law. Rather than being fundamental features of reality, mathematical relationships might be emergent properties of how information is processed and projected in higher dimensional spaces. Different regions of the multiverse might literally operate according to different mathematical principles. Cosmic inflation itself might be better understood as a holographic projection process. The rapid expansion of space during inflation could be the mechanism by which three-dimensional spacetime is projected from the expanding boundary surface of an inflating holographic system. The quantum fluctuations that seed galaxy formation might be holographic interference patterns in this cosmic projection process. The measure problem, how to define probabilities in an infinite multiverse, becomes even more complex when that multiverse consists of holographic projections. The relative probability of different holographic realities might depend on the information processing capacity of their boundary surfaces or the computational complexity of their projection processes. Recent advances in holographic duality have shown that some holographic boundaries can project multiple bulk spacetimes simultaneously, depending on the quantum state of the boundary system. This suggests that the relationship between boundaries and projected realities might be far more flexible than originally thought, with single boundaries capable of supporting entire ecosystems of interconnected holographic universes. As you contemplate your existence within this vast holographic multiverse, consider that your consciousness might be participating in something far grander than the already magnificent time, perhaps more than any other aspect of reality, transforms radically when viewed through the lens of holographic physics. The flowing river of moments that seems so fundamental to your experience might be an illusion created by the way information is processed in a cosmic hologram, an emergent property rather than a basic feature of existence. In conventional physics, time is often treated as a dimension similar to space, forming the four-dimensional stage of space-time on which physical events unfold. But the holographic principle suggests something far more radical, that time itself might be emergent from timeless information processing occurring on the boundary of our cosmic horizon. This emergent view of time begins with a startling observation about the mathematics of holographic duality. The theories that describe the boundary surface, where all the information of our universe is supposedly encoded, are often timeless. They describe patterns of information and their relationships without reference to temporal flow or sequence. Yet when this timeless boundary information is projected into the holographic bulk space that we experience as our universe, it creates the appearance of temporal evolution. The projection process itself generates the experience of time flowing from past to future, even though the underlying boundary information exists in a timeless mathematical relationship. Think of this like a movie reel containing all the frames of a film. The reel itself doesn't change or flow, it simply exists with all frames present simultaneously. But when projected through appropriate machinery, it creates the experience of motion, narrative, and temporal development for viewers. Similarly, our cosmic boundary might contain all moments of our universe's history simultaneously, with the holographic projection process creating our experience of temporal flow. This perspective explains one of the most puzzling features of quantum mechanics: the measurement problem. Why do quantum systems exist in superposition until measured, and why does measurement seem to select one outcome from many possibilities? In a holographic universe, measurement might be the process by which timeless quantum information on the boundary gets projected into specific temporal sequences in the bulk space. The arrow of time, the fact that we remember the past but not the future, that entropy increases rather than decreases, emerges naturally from holographic information processing. The projection process that creates our temporal experience might have a preferred direction based on how information flows from the boundary into the bulk space. This creates the asymmetry between past and future that characterizes our experience of time. Quantum entanglement takes on new meaning when time itself is emergent from holographic processing. Einstein's concern about spooky action at a distance dissolves when we realize that entangled events might not be separated in time at the boundary level. What appears as instantaneous correlation across space might reflect the timeless relationships encoded in boundary information. Causality itself becomes more subtle in a holographic universe. The cause and effect relationships we observe in our three-dimensional experience might be approximations of more complex information processing relationships occurring in the boundary theory. Events that appear causally connected in time might be connected by patterns in the timeless boundary information that project into temporal sequences. This has profound implications for our understanding of free will and determinism. If time is emergent from timeless boundary information, then the future isn't predetermined in the usual sense. It's encoded in potential form on the boundary, waiting to be actualized through the holographic projection process. Conscious choice might be a real causal process that influences how potential information becomes actual temporal experience. The block universe concept, from relativity, the idea that all moments of time exist simultaneously in space-time, finds new interpretation in holographic theory. Rather than past, present, and future all existing equally in a four-dimensional block, they might all be encoded simultaneously in the timeless boundary information, with temporal sequence emerging only through the projection process. Retrocausality, the possibility that future events might influence past events, becomes less mysterious in a holographic framework. If all temporal information is encoded simultaneously on the boundary, then influences can flow in any direction through the timeless relationships, even though they appear as forward or backward causation when projected into temporal experience. The relativity of simultaneity, Einstein's discovery that different observers disagree about which events occur at the same time, might reflect different ways of slicing the timeless boundary information into temporal sequences. Each observer's reference frame corresponds to a different way of organizing boundary information into the experience of temporal flow. Quantum field theory's treatment of virtual particles becomes more intuitive in emergent time. Virtual particles, which exist for extremely brief periods and can even travel backward in time, might represent the way that timeless boundary information gets temporarily organized into particle-like patterns during the projection process. The grandfather paradox and other time travel puzzles dissolve in a holographic universe. If time is emergent rather than fundamental, then time travel in the usual sense becomes impossible. You can't travel to a when that doesn't fundamentally exist. However, the timeless boundary might contain information patterns that project into multiple, consistent temporal narratives. The beginning and end of time also take on new meaning. The Big Bang might not be a moment when time began, but rather the projection of boundary information that creates the appearance of a temporal beginning. Similarly, the universe's ultimate fate might be encoded in boundary patterns that project into far future scenarios. This emergent view of time also connects to the fundamental role of information in quantum mechanics. The quantum mechanical description of time evolution through the Schrödinger equation becomes a description of how timeless information patterns project into temporal experience. The wave function collapse associated with measurement becomes the process by which potential temporal sequences become actual experienced moments. As you experience the flowing of time right now, the progression from word to word as you read this, the gentle drift towards sleep, the sense of moments building upon each other, consider as our journey through the holographic universe draws to a close, we find ourselves in a place that is both utterly familiar and completely transformed. You are still you, reading these words, breathing gently in this quiet moment. Yet, everything about the nature of that experience has been revealed in a new light. You are not a collection of particles moving through empty space. You are a pattern of information, beautifully complex and profoundly interconnected with the very fabric of reality itself. The holographic principle has shown us that the solid, three-dimensional world we inhabit emerges from information encoded on a distant two-dimensional boundary. This isn't a reduction of reality to mere data, it's an elevation of information to the status of the fundamental building block of existence. You are made of the same stuff as thoughts, as mathematics, as the relationships between ideas. You are a conscious pattern in the cosmic information field. This transformation in understanding doesn't diminish the meaning or beauty of existence. It reveals that meaning and beauty are far more fundamental than we ever imagined. Love, creativity, consciousness, and wonder aren't accidental byproducts of complex information processing. They might be essential features of how the universe processes and organizes information into experience. The scientific evidence for holographic reality continues to accumulate across multiple fields of physics. From the mathematical elegance of holographic duality to the experimental searches for space-time granularity, from the quantum information foundations of entanglement to the cosmological mysteries of dark energy, the holographic principle provides a unified framework for understanding disparate phenomena. It connects the smallest scales of quantum mechanics to the largest scales of cosmology, revealing deep symmetries in the structure of reality. The mathematics underlying holographic physics possess a beauty that transcends mere utility. The equations that describe how two-dimensional information projects into three-dimensional experience are not just calculational tools, they're poetry written in the language of physics, expressing truths about existence that touch the deepest levels of meaning and understanding. Living with the awareness that you might be a holographic projection changes your relationship with yourself and the world around you. The boundaries between self and universe become more fluid when you realize that your information is distributed throughout cosmic space, encoded on a boundary so distant that light from it could never reach you. You are simultaneously infinitely small and infinitely large, a localized pattern in a cosmic hologram. The holographic perspective also transforms our understanding of consciousness and personal identity. Your thoughts and experiences aren't trapped inside your skull. They're part of a vast information processing network that extends to the edge of the observable universe. Every moment of awareness participates in the cosmic computation that creates and maintains reality. The implications for human connection become profound when viewed holographically. If all consciousness arises from information processing within the same cosmic hologram, then the boundaries between different minds might be less fundamental than they appear. Empathy, love, and understanding might reflect genuine information connections between different patterns of consciousness within the holographic framework. The temporal aspects of holographic existence reveal that your relationship with time itself might be far more creative than you imagined. If time emerges from the information processing that creates the holographic projection, then your conscious experience doesn't just observe the flow of time, it participates in creating that flow. Every moment of awareness contributes to the ongoing process by which timeless information becomes temporal experience. The creative potential inherent in holographic reality is extraordinary. If the universe operates like a vast quantum computer processing holographic information, then creativity, insight, and innovation aren't just human activities, they're expressions of the fundamental creative capacity of reality itself. When you have an original thought or insight, you're participating in the universe's exploration of new ways to organize and process information. The environmental implications of understanding our holographic nature are equally profound. If everything you perceive, the natural world, the atmosphere, the vast ecosystems of Earth, emerges from the same holographic information processing that creates your consciousness, then environmental destruction becomes a form of self-destruction. Caring for the planet becomes caring for the holographic system that creates and sustains your existence. The future of holographic physics promises discoveries that will further transform our understanding of reality. Experiments with increasing sensitivity will probe deeper into the quantum structure of space-time. Advanced quantum computers will simulate holographic systems with unprecedented accuracy. New mathematical techniques will reveal deeper connections between information theory and fundamental physics. Yet perhaps the most important discovery is one you can make right now, in this moment, as you contemplate these ideas. The recognition that you are a conscious information pattern in a cosmic hologram doesn't require sophisticated mathematics or advanced physics. It only requires a shift in perspective, a willingness to see yourself and reality in a new way. This shift in perspective has practical implications for how you live and relate to existence. When you realize that your consciousness is part of the cosmic information processing that creates reality, everyday activities become opportunities to participate consciously in the universe's exploration of its own possibilities. Work becomes a way of organizing information into useful patterns. Relationships become exchanges of consciousness within the holographic network. Art and creativity become expressions of the universe's aesthetic exploration of its own information space. The holographic principle also provides a framework for understanding suffering and healing. If consciousness emerges from information patterns, then psychological and spiritual healing might involve reorganizing those patterns into more harmonious configurations. Trauma might represent disrupted information flow, while healing represents the restoration of healthy information processing. The search for meaning in a holographic universe leads to a beautiful paradox. The more we understand about the information-theoretic nature of reality, the more meaningful existence becomes. Far from reducing consciousness to mere computation, holographic physics reveals that computation itself is a fundamentally creative, consciousness-generating process. As you prepare to sleep and dream tonight, carry with you this transformed understanding of your place in reality. Your dreams might represent the natural way consciousness processes information when freed from the constraints of sensory input. The boundary between waking and dreaming might be far more fluid than you realize, with both states representing different modes of holographic information processing. The holographic universe doesn't diminish the mystery of existence, it deepens it infinitely. Every moment of consciousness, every experience of beauty, every feeling of connection and love becomes a miracle of information organization, a temporary crystallization of meaning in the vast flow of cosmic information processing. You are not a separate observer of a holographic universe. You are a conscious participant in the holographic computation that creates reality itself. Your awareness, your thoughts, your capacity for wonder and understanding are not accidents, but essential features of how the universe explores and expresses its own infinite creative potential. Rest now in this understanding. Let these ideas settle into the deep patterns of your mind, integrating with the holographic information processing that creates your ongoing experience. Dream of information patterns dancing in spaces beyond dimension, of consciousness as the universe's way of knowing itself, of the beautiful mathematics that transforms abstract relationships into the lived experience of being. Sleep peacefully, knowing that you are both the observer and the observed in the cosmic hologram we call reality.